The cost to get a payload to space has always been a driving force for rocket innovation. Economical, reusable designs like the Falcon 9 aid drastically in lowering the cost of putting payloads in space. But these heavier reusable designs take payload capacity away from the rocket. Now, considering that rockets are generally 80% fuel at liftoff, and the further we want to go, the more fuel we need, could we save on fuel by instead stealing energy when we are already in outer space? Fortunately, we have found a way to steal energy from planetary mass objects, or planets and moons, to compensate for that required fuel that would otherwise have to come from Earth. But how? All objects have a sphere of influence from their gravity, demonstrated here by the planet's blue glow. This is an area where objects, if they enter it, will be pulled towards them. But how the passing object, like the Voyager 1 in this example, is affected depends on how close it is to the planet and how big the planet is. Kind of like two magnets, where their strength and distance apart determines how they interact with each other. But now, how can we pass by a planet in a way to steal energy from it? Let's look at an example starting from an orbit around Earth. Say we are here on Earth and we want to explore the solar system. Well, we first need to leave Earth's strong gravitational field. Having no choice but to use rockets, we will need a speed of 11.18 kilometers per second. But now we are orbiting the Sun as Earth does. To raise our orbit higher, we would need more fuel. But what if we get pulled into another planet's gravitational field? Here, a Voyager spacecraft is approaching a static planet. The teal and dark blue arrows coming from the spacecraft represent the gravity experienced by the spacecraft. As we approach the planet, our speed will increase on both axes. But as we pass the planet and fall away from it, gravity will continue to pull the spacecraft towards the planet and slow it back down. All the speed we gained while falling towards the planet on the approach, we lost on the retreat, as we fell away from the planet by still being under the influence of its gravity. This is very much like a roller coaster entering a dip on a track. This therefore leaves us with no added speed relative to the planet we interacted with. But this specific interaction with static planets is not realistic, as the planets in our solar system are in orbit around the Sun. Therefore, they are always in motion. Taking this into consideration, let's look at this interaction again. On the approach of the planet, both axes are accelerating, just like before. We then pass the horizontal axis, where we begin to decelerate on the vertical axis. But as you can see, there's no retreat on the horizontal axis, as the planet is staying ahead of the spacecraft, continually pulling it along. The end result is we have added energy to our spacecraft. But now, where does this extra energy come from? The law of conservation of energy states that energy cannot be created or destroyed, but did we just create energy? Well, just like the magnets affecting each other like I mentioned before, the spacecraft also has a gravity field from its mass and pulls back on the planet throughout the interaction. A great example of this is the Moon and Earth. Earth's gravity keeps the Moon in a 27-day orbital period, but the Moon's gravity creates the ocean's tides here on Earth. So as long as the planet is pulling the spacecraft along, the spacecraft is pulling the planet back, slowing the planet down. Now, because of the difference in size, the change of speed for the planet is negligible. For example, Voyager 1 weighs only 721 kilograms, and Jupiter weighs a lot more. The result of this gravity assist will increase the spacecraft's speed by 10 kilometers per second, and slow down Jupiter by roughly 10 to the power of negative 24 kilometers per second. This is a gravity assist and can be used not only to speed up a spacecraft, but also slow it down. This is done by approaching the leading edge of a planet like this. Now, instead of the planet pulling you along, adding to your speed, it's pulling you back, slowing you down. Although gravity assists have been made popular by the Voyager program that launched back in 1977, gravity assists are still being used today. For example, the Artemis program demonstrated here used gravity assists to slow down the spacecraft on approach to the Moon and speed up when returning back to Earth. If you enjoyed this animation and would like to see others, please consider subscribing. Thanks for watching, and I'll see you on the next one.